So welcome to Math 150, Multivariable Calculus, Spring 2021, Lecture 4. And so today we're going to be talking about equations of lines and planes and other things. So as always, if there are topics you want me to discuss, let me know, preferably in advance. But I should be able to do this on the fly. If not, you can have a full refund for Louis' card. All right. So one of the questions that somebody asked me to talk about is actually from a homework problem that's due on Monday, but that's absolutely fine. And you have a 4, 5, 6 triangle, and they wanted to know what was the cosine of the largest angle. I remember years ago when I was young, I saw a special on teachers in Massachusetts who make a difference. And on the blackboard, I think it had this as a triangle. 4, 6, 10 triangle. Anybody notice anything about a 4, 6, 10 triangle? Yes. It should not exist. If you think about here's a line of size 10, and I draw a circle here of radius 4, any point on that circle is 4 units from the point. And if I draw a circle of radius 6 from here, any point on that circle is 6. The only way that they can hit is if it's a flat triangle. So this is a nice result of all triangles. The sum of any two sides has to be greater than the third. So the first thing when I see a 4, 5, 6 triangle, I ask, can it exist? Yes. And then the question is, can we construct it? What does it look like? How unique is it? Well, when I have a 4, 5, 6 triangle, I know without loss of generality that if I give you any side, then if I give you the side of length 6, the side of length 4 has to be coming from one way and the side of length 5 from the other. And if you don't like the way I've oriented things, just flip the universe. So without loss of generality, I can assume I have a segment of length 6 here, and then I can assume the side of length 5 is coming up from here, and the side of length 4 is coming from there. And so I can draw the triangle. So here is drawing a circle of radius 5, and here is drawing a circle of radius 4. And so there will be a unique triangle that can be formed. How could we find the angles? What can we use? Law of cosines. The law of cosines will give us the angles. And when you look at this, there's only going to be one possible triangle. So how many of you remember the following? We'll see if you use the same terminology as when I was CPCTC. Corresponding paths of congruent triangles are congruent. They have all these 3-letter phrases using just A's and S's. And depending on which one you write down, it is a legitimate way to tell two triangles are similar. So one of the ones that is, somebody want to give me something that's legitimate? Side angle side is legitimate. So if I give you a side over here, and I give you an angle, and I give you another side, well, I have no choice except I have to complete it like that. So if I give you two sides and an angle between them, we're good. Which one is not valid? Please give me the letters rather than saying it. Angle, side, side. Don't make an ass of this, right? So if I give you angle, side, side, how bad is it? Well, here's a side, here's an angle, and then so we'll just draw this going off to infinity. And now we know this side, and I know the side coming from here. What does it mean to know the side coming from here? It means I draw a circle with that as the radius, and I see where it intersects with line. the side length is too small, can it intersect the line? No. So if the side length is too small, there will be no such triangle. As I increase the length, what will eventually happen? Before it crosses the line at 2 points, what will happen then? So if I go at the right angle here, that is the first distance where there's going to be an intersection. There'll be exactly one intersection. And then as I go beyond that, let's say I go up to here, I'll now have two possible triangles. So once the distance becomes sufficiently large, I have two possible triangles. Will I always have two possible triangles? Well, if I start getting even larger, I'm going to just have this point moving towards infinity. That's still going to be there. And this point here is going to just start moving down. So you might say at one point over here, I no longer have a real triangle because I'm using that side twice. But you'll in general have two possibilities. So I was just throwing an old joke. You should never assume, because when you assume, this is what happens. Okay? This is actually a really good question to lead into what we want to do today, which is study the equations of lines. And so here we have a line. We have a line starting at this point, going off at an angle. So this is a slightly different way of talking about the equation of a line. Normally, when you think of a line, what do I give you? What information? Yes. Okay. So one is point and direction. You normally say direction you normally say slope, but it's better to say direction. So that's one way to do a line, the point direction. What's another way to do a line? 2 points. So one point, and there's one other way. Slope intercept. If I give you the slope and the intercept, which one of the three do you want to use? Yeah, slope intercept. If I give you 2 points, which one do you want? Point. So depending on what information I give you, sometimes one is more convenient than the other. And so here, how would we do it with point direction? We would go y minus y naught equals m x minus x naught. And that's how we would do it with, I give you a point and I give you a direction. I give you a slope. Point is I first calculate the slope is x1, is y1 minus y naught over x1 minus x naught. And now that I have that, then I go back and I use point direction. I could write it down directly as y minus y naught equals y1 minus y0 over x1 minus x0, x minus x naught. And when you look at this, what's a really good value of x to plug in? I'm sorry? Not 1, not 0, x naught. If I take x equals x naught, this vanishes. The right side becomes 0, and I get y equals y naught. So if x equals x naught, then implies y equals y naught. What's another good point to take for x? So one was if I take x to be x naught, this whole expression is 0. There's one other good choice for x. x1, because if I take x1, I have x1 minus x naught over x1 minus x naught. It's going to cancel. Not surprisingly, because these are the 2 points I'm given. I'm given the point x naught and x1. I know things about those points. Let me plug them in. if x equals x1, then this becomes y1 minus y0. So y minus y0 equals y1 minus y0. In a dazzling beat of algebra, I get y equals y1. So we could write it down explicitly like this, or we could say, well, look, once we have this, let's just calculate, call that m, and put that in. Either way is fine. The last is the slope intercept. This is y equals mx plus b. And so the slope is m, and the intercept is the point 0b. So it's where the line crosses the y-axis. Where you hit the y-axis. Okay. So any questions about those three equations of lines? So then we want to figure out how should we generalize these to higher dimensions. And in the course of doing this, we will revisit some results from calculus, and we're going to put a little bit of material in the bank. We should all have seen the definition of the derivative. It's not immediately clear how to generalize the definition of the derivative to several variables. This is something that is typically glossed over in most multivariable math classes, especially freshman multivariable math classes, first-year multivariable classes. It's not worth going into full excruciating detail, but it's worth doing enough to know that we have to be careful. That when we have several dimensions, we have more freedom. It's not immediately clear how things should generalize. So let's draw a picture. I love pictures. I can draw them. Here's my point x0, y0. And here's my slope. So can someone tell me what slope means? So what is the slope of the line? Yes. Change in y over the change in x. So if I move to another point, I see how much y has changed and how much x has changed. So for example, if I have a point here, x1, y1, the change in y is y1 minus y0, and the change in x is x1 minus x1. If you could choose how much you want x to change by, what would you change x by? One. So if the change in x equals 1, then the slope is just the change in y. So another way of doing that is if I increase x by 1, then my y value increases by m. So in that case, this is 1, this is m. How would you write the slope vector? If you want to write this as a vector, what would the coordinates of the vector be? If you want, you can view this as the origin, 0, 0. We moved over 1 unit, and then we moved up m units. So what would the vector be?
1, 3.
I'm sorry?
Oh, 1m.
1m. And this is the nice thing about having the component being 1. Can we always assume that it's changing by 1? What's the one time I can't do that? You're right, there's one line where I can't assume x changes by 1. Yeah, when it's vertical, perfect, right? If it's vertical, I can't move x by 1. The equation of the line is x equals 5, or something like that. And so if x equals 5, you are not allowed to change it. Later in the semester, we will be talking about regressions and statistics. And the only time things fail is if you are a complete moron and want to investigate how something depends on something else and you don't allow that something else to change. So I want to determine how the time it takes to roll down an inclined plane depends on the angle, but I'm only going to measure things at 30 degrees. I'm going to try to then extrapolate from my data how things depend on various angles, only measuring things at 30 degrees. You can't do that. You need to allow the angle to change if you want to make any inference. So here, if my line is vertical, I have a problem. Anything else, I can always adjust and say, I'm going to move x 1 units and then see how much y changes. So a lot of times, we like to write our equations of a line as maybe x of t, y of t. And so you give me a time, and I tell you where we are. So I will often give you an initial point, x naught, y naught. That's where we start. And then we have our direction vector. T times our direction vector. So in the plane, our direction vector is 1m. So let's just assume we don't have a straight line. So let's just assume right now that we have these 1 and m. And let's unwind this. We get x of t is x naught plus t. Y of t is y naught plus mt. Normally when we do equations of lines in the plane, we don't have a parameter t for time. We like to study how things change in time, but in the plane we might just be physically write down the equation y is a function of x. Well, I can replace t with x. What is t equal? So if x of t is x naught plus t, what would t equal? X of t minus x naught. And then we can substitute that in here. And we get y of t is y naught plus m x of t minus x naught. Well, if you want just y equals y naught plus m x minus x naught. Does that look familiar? This is about as far as we can go and keep everything on the board. You just squeeze it in. This is the standard equation of a line. This is point slope. The most popular, the first one we listed. But this shows us a nice way to generalize point slope to several variables. Is we now have a vector of movement. And we can say, if I change x by 1, how much does y change? How much does z change? Now, the problem with that is we are making x direction special. There's nothing wrong with making the x direction special, except when. So when is it bad to be making, what line is bad to have the x direction special? I already mentioned it. The vertical line. If we have the vertical line, having the x direction special is bad because we can't change it. It's better to just write it as x naught y naught plus t times some vector. So the equation of a line is x of t, y of t is x naught y naught, our initial point, plus t times v. Or if you want, it could be P naught, our initial point, plus T times V. You can use lots of different notations. Any of them is fine. And this gives us the equation of a line through a point. I'm going to erase our different definitions of lines. And so in general, is the origin of the universe. Here is some point P. And now here is a line going through P. And here is a vector V that's telling us the direction of the line. So if I'm going to give you a line, I have to give you two pieces of information, a point and a direction. And so we could say, if you wanted to, P at some time T is P of P times Z. Something like that would be the equation of the line. If you want to write it out in excruciating detail, you could say x of T, y of T, z of T, if you're in 3 dimensions, is x naught, y naught, z naught, or maybe px, py, pz, doesn't matter, plus t times maybe px, py, pz. How many dimensions is a line? One dimension. How many dimensions is a plane? How mmany dimensions is 3 space? Okay. So a line actually have one free parameter. Once I give you that value, everything should be determined. Over here, once I tell you what x is, y is now known. Once I tell you what t is, everything is now known. So this is the equation of a line. What is 3 times 5? 7 times 7. 8 times 2. 0 times infinity. All right, 0 times infinity. Let's do that one again. Anybody want to hazard a guess? Why 0? Anything times 0 is 0. So by the rule of anything times 0 is 0. 0 times infinity is 0. Anybody else want to give me an answer? It could be infinity. Infinity is the biggest thing possible. If I look at the limit as x goes to 0 of x squared times 1 over x, what does that equal? That's the limit as x goes to 0 of x, which is just 0. Right? But x squared is going to 0. What's 1 over x going to? So I can't just say the limit of a product is the product of the limits. I can do that if the limits are finite. I can do it if at least one of the limits is finite. But if one of the limits is infinity and the other one is 0, I can have some trouble. What if instead I look at the limit as x goes to 0 of x times 1 over x squared? That's the limit as x goes to 0 of 1 over x. What does that equal? I'll make it x cubed. Just make it. That goes to infinity. But now I've got 0 times infinity. So here 0 times infinity was 0. Here 0 times infinity was infinity. If I do the limit as x goes to 0, anybody want to give me their favorite number? What was it? 12? 5. 5x times 1 over x. What would that limit be? It would just be 5. So I can make 0 times infinity anything I want. I'm going to show you a very strange number that's 0 times infinity. I'm going to prove to you it's -1. Anybody remember anything from the theory of lines involving -1? So we will be doing a lot with sequences and series later in the class. This was a good way to just review a little bit of limits. We will be using limits when we do derivatives. So it's good to start refreshing ourselves on these rules. So plane 0 times infinity equals -1. Okay, you ready? Let's take two lines that are perpendicular. Okay? Without loss of generality, where do they intersect? At the origin, of course they intersect at the origin. I can't just say without loss of generality they're oriented like this, but I can at least say they intersect at the origin. Alright? So here is my first line. And I'm going to take a line that's perpendicular to it. I'm going to assume this is the right angle. So this is theta. What are the coordinates of this point? Cosine theta tan theta. Perfect. Does this look familiar? Choosing the origin to be the center, choosing a unit vector. We've done this many times. We've done it so many times it's now a technique. We're trying to simplify the algebra. Okay, so we've got the first point is cosine theta sine theta. What are the coordinates of this point? I'm sorry, what was that? Why is that? So this angle here is what? Not theta. What is this angle here? 90 minus theta. The whole thing has to be added up to 180. This is 90, this is theta. This is 90 minus theta. So we can represent this point two different ways. We could write it as, cosine of 90 plus theta, sine of 90 plus theta. Or we could try to do things in terms of the triangle here. So if this is 90 minus theta, then that has to be theta over here. So what does this height have to be? Cosine theta. And what does the width have to be? Almost like minus sine theta. So this point is minus sine theta cosine theta. Okay. Is everybody comfortable with how we get those coordinates? There's many different ways you can do it, and we need to do a little bit of trick. But this is a great way to review trick. I can write it as 90 plus theta. I can use 90 minus theta and work with it like that. I can use my trick identities. Cosine of x plus y is cosine x, cosine y, minus sine x, sine y. Sine of x plus y is sine x, cosine y, plus cosine x, sine y. If you're looking for things to memorize, these are two really good identities to know. And later we'll show how to divide them quickly. But now if I take, say, y to be 90 degrees, cosine x, cosine 90. What's the cosine of 90? You always draw your circle. The cosine of 90 is going to just be 0. What's the sine of 90? 1. So since the cosine of 90 is 0, this piece vanishes. The sine of 90 is 1, so you just get negative sine x. Ah, good, that's what we had over here. So if you can just remember and draw your circle here, you can often figure out how to handle these shapes. All right, so we have two perpendicular lines. So I'll call this line L1, I'll call this L2. L1 is perpendicular to L2. Do people remember that symbol for perpendicular? So what is the slope of L1? So what's the slope of the first line? Tangent theta. And if you do it all a little bit longer, it is. So change y sine theta over cosine theta, and that is tangent to theta. See how nice it is that everything's on the unit circle? What's the slope of L2? Negative cosine theta over sine theta. How should I write that? I could write it as negative cotangent. I'm going to write it as negative 1 over tangent theta. Do you notice any relationship between the slopes? They're reciprocals. Yeah, so if I look at the slope of L1 times the slope of L2, what do I get? Negative 1. How many of you have seen this result from algebra 2? The product of the slopes of perpendicular lines is negative 1. This is actually extremely useful because if you know a line and you want to find a line perpendicular to it, it tells you the slope. It's a really nice result. Is everything okay here? Are there any angles that scare you? I have a history of glossing over small technical things. What angle might scare you? So when might you be afraid with sine theta over cosine theta? What's the bad angle? 90 degrees. So theta equals 90 degrees or what else? 3 pi over 2 or 270 degrees. But of course, we might as well assume that our point is in the upper half. Because if I have a line, I can always choose the upper half. So I'm worried if theta is 90 degrees. Over here, we're worried that theta is equal to what? 0 degrees or 180 degrees. What do those correspond to? The standard xy axis. What's the slope of the lines when they line up like this? What's the slope of the horizontal line? It is 0. What's the slope of the vertical line? Undefined, or, yeah, give me infinity. So let's look at what's going on. I have 2 lines, and if they're perpendicular, the product of the slopes is negative 1. Product is negative 1, product is negative 1, product is negative 1, and I keep going, and all of a sudden they align with the coordinate axis, and it's undefined. And then as soon as I no longer align, it's back to negative 1. So it's negative 1 everywhere, but at that one point when there's a line. So in that case, how would you define for this problem 0 times infinity? I would define it as negative 1 for this problem. The slope is always equal to, the product of the slope is always negative 1 until I get to here, it's undefined, and it's defined again to be negative 1. It seems reasonable to extrapolate it to be negative 1 every time. So this is a nice way to review some equations of lines, some beautiful properties, to see a little bit of limits, to review our trigonometry. If I give you the limit as x goes to 2, x squared minus 4 over x minus 2, are you a little bit worried when you see this? Yeah, the denominator is blowing up. And what's the numerator doing? The denominator goes to 0, so it's making the whole expression blow up. And what's the numerator doing as x goes to 2? What does x squared minus 4 look like as x goes to 2? 0. So I have 0 over 0, it's undefined. Does anybody notice something you can do with x squared minus 4? Factor it. So this is the same as the limit as x goes to 2 of x minus 2 times x plus 2 over x minus 2. Gee, what should we do? Yeah, let's just cancel the damn x minus 2's. And this is just the same as x plus 2. So what's the limit going to be? 4. So the limit makes sense. Even though we have something that's looking like 0 over 0, when we take a limit, the way this works is it's all x getting closer and closer and closer to 2, but x is never equal to 2. It just gets arbitrarily close. That's one of the key ideas in calculus. When we do these limits, it's not equal, it's just very close. Okay. So any questions on what we've done so far? So again, I'm just trying to give you a sense of where these equations for lines come from. Equations for planes are a little bit more involved. How many directions does a plane have? 2. And so if you want to generalize this to a plane, it's basically, I still need a point like I had for the line. So I have my point P, and now I have 2 different directions. Here's my direction V, here's my direction W, and I'll have something like that. So the simplest equation for a plane would be, maybe P of T is, we'll call it P naught, plus T times B plus S times W. What's the easiest value of T and S to understand? So what would be the best values of T and S to plug in? Not 1, 0. If S and T equals 0, this whole thing vanishes. Oh, actually, this should be P of T. 2 reasons. So if I look at P of 0, 0, that's just our point P naught, which should be in the plane. Excellent. What if I take S to be 0? Then it gives me the line in the plane in the direction of V. If I take T to be 0, I have the line in the plane in the direction of W. So the equation of a plane is very similar to the equation of a line. Point plus T times direction. Now we have point plus T times one direction plus S times another direction. Do you have more than one choice of directions that you can use? So if I give you a plane, do you have more than one choice of direction? Yeah. What's a good choice of direction? It's one of the few things I will give credit to New York City. Yeah, north, south, east, west. Yeah, Williamstown is very nice. What's a really good east-west marker in Williamstown? Route 2, right? You ever seen the movie Pleasantville? The geography is not that complicated in the town of Pleasantville. We've got Route 2. And then Route 7 is basically coming in perpendicular. That gives us a roughly on one side. You can choose other coordinate systems. So instead of just doing 2 things like this, I could do something like this. You give me any point, let's say I want to get to here. I flow along this line to get to the right height, and then I use this to go backwards to get to there. And your linear algebra, you'll spend a lot more time on this. But as long as I have 2 vectors that are in the same direction, they will give me a plane. If I have 3 vectors, I want to make sure that they don't align. So I want to make sure no vector lives in a space spanned by the other 2. So 2 vectors that are parallel will give me a plane. I just need my 3rd vector to be outside of that plane. A good way to see if the three vectors are really full, is to take the determinant. And so we can calculate a hyperplane. You know, TV plus SW plus, and we're coming up. I need to put in another letter and another vector. And that's why some people say, rather than doing it like this, let's do it as maybe T1, T2, T1, V1, T2, V2. Because if I do it like that, I can extend to another direction very easily. Now it's just T3, V3. And you can see that for a plane, I have two free parameters. It's going to give me a two-dimensional object. Okay. So any questions on planes from the stuff you've read in the book, the stuff from the video? Yes? So what was the question about hyperplane?
What is it?
So a hyperplane would be one higher dimension. We sometimes will use the phrase hyperplane to be anything of dimension 3 and greater that's not the full space. So if I'm in a 4-dimensional world, I could have a 3-dimensional hyperplane living in the 4-dimensional world. If I have an 8-dimensional world, I could have, plane is going to be 2 dimensions. I could have hyperplanes of dimensions 3, 4, 5, 6, 7. And the theory is basically the same. I'm just adding more variables, I'm adding more indices. Once we understand the line, we see how the line generalizes. We just add more stuff. And then, similar to how at the start of the day we have all these different ways to come up with equations of lines, we have lots of different ways to come up with equations of planes. It depends on what information I give you. Now, one way to view a plane is it's all points that start from a fixed point and is perpendicular to the normal direction of the plane. So the normal is coming out of the plane. Everything in the plane is going to be perpendicular to that. All right, let's think a little bit about what that means. So, we have a plane, we have a point, and we have a normal direction coming up. We might assume the normal has direction coming out of the plane that has length 1, but maybe it doesn't have length 1. One way to view the plane is, this is the point, say, x0, y0, z0. I take any other point in the plane, x, y, z, and I look at the line, the vector from x0, y0, z0 to x, y, z. And that has to be perpendicular to the normal. And if you think about it, we start off with the 3-dimensional world. If I tell you you have to be perpendicular to the normal, how many dimensions is the space that's perpendicular to the normal? So here's my normal, and I take something that's perpendicular to it. I can spin this point around. It's going to give you what kind of object? Plane. So this is another way to view the equation of a plane, is I specify a normal direction, and I just take all the things that will be perpendicular. So if my origin is over here, here's my two vectors, that line there has to be perpendicular. So I would want x, y, z minus x0, y0, z0 is perpendicular to the normal. And we often have the normal as vector AB. Only I knew how to tell if a vector was perpendicular to another vector. That would be so useful right now. Do you know any way to tell if vectors are perpendicular? What do you do? Dot product. So what is true about two vectors dot product if they're normal, if they're perpendicular? It's 0. So we want x minus x naught, y minus y naught, z minus z naught, dotted with a, b, c, and is it 0 the number or 0 the vector? 0 the number. So we get a x minus x naught plus b y minus y naught plus c z minus z naught equals 0. And that's another way of writing down the equation of a plane. And this is where I'm giving you the normal and I'm giving you a point. Okay? You can also write this as ax plus by plus cz equals p dotted with normal, p naught dotted with normal. So if you just bring the ax naught, b, y naught, c, z naught over to the other side, it's actually just p naught dotted with normal. Okay. One of the things we're learning today is that I can often give you information in many different ways. And depending on how I give it to you, sometimes one way is better than another. So when I gave you equations of a line, the second thing we said, left of the silver medal, was point, point. And what's the first thing we did with point, point? What did we calculate? We calculated the slope. So this is a pretty nice formula for the equation of a plane. It's a x minus x naught, b, y minus y naught, etc., etc. Maybe I really like this equation, but unfortunately, I'm now giving you some point p naught, and I'm giving you two vectors v and w. Can anybody think of a way to get a normal vector knowing v and w? Yeah. So n is just v cross w. And this is a beautiful application of the cross product and how lovely it is to live in three-dimensional space. Does it matter if the normal is unit length? No. If I multiply a, b, and c by 5, it doesn't change the equation. I've just multiplied the left side by 5. Well, I can multiply 0 by 5 and not change its value. So I don't need to have a unit length. But let's say I'm worried because there are some formulas that involve the normal vector, and it might assume later that I chose the unit vector. What could I do to make this have unit length? Yeah, I can divide it by the length of v cross w. And if I do that, I now have something of unit length. And so if I want to write down the equation of a plane using a normal vector, I can actually calculate the normal vector if I have the two directions. If I have the normal vector and I have one vector in the plane, I could actually take their cross product and get another direction in the plane. So there's lots of ways to go back and forth between the various things, depending on what you have. The whole goal is to try to make things easy. And so I will end with a challenge. Anybody know what this means? It's the keyboard. Why is the keyboard structured the way it is? It's to slow you down. How many of you knew that this keyboard was designed to slow you down and to be inefficient? Not bad. In the old days, when people typed quickly, they would have little things that would be going down and making marks on the paper. And if you hit two keys that were in close proximity quickly, they would often lock and jam. So they deliberately designed this to try to make you alternate between your fingers and to slow you down. There are many, many typewriters that are better than the QWERTY keyboard. Dvorak is the one that I think professional typists use. Why have we not switched from the QWERTY keyboard? Who's Who's used to it? The older people are used to it. What would be required to switch to a new one? The older people would have to learn something new. It's much easier to just keep propagating this down. If we truly loved you, we would have taken the hit and learned how to use a better keyboard. Does it make any sense in the electronic age to have a QWERTY keyboard? I will assume everybody here has sent at least one email in their life, given that you had to email me your thoughts on Michael Islam's speech. How many of you have ever sent an email to more than one person? And how many of you have ever sent an email where there's one person who's primary and there's a bunch of other people who you just want them to get? So what do you do if you want other people to get it but they're not primary? Okay, what does CC mean? Carbon copy. Why is it called carbon copy? Does anybody know why it's called carbon copy? So you've all been emailing for years, you've all been doing carbon copy, you have no idea why you're doing carbon copy? So they used to print it out and they would have special paper where you would have several sheets, and if you wrote very, very hard, it would veer down and it would make multiple copies. And these would be the carbon copies. Sometimes in old tourist places where they don't have all the electronic systems, they still have receipts that are done that way. Again, 21st century, does it make sense to talk about a carbon copy? No. They've changed this, and sometimes people now call it courtesy copy rather than carbon copy to adjust for the 21st century. But you always want to think about what you're doing and why. What's the notation? Why are we doing it? And so here, the idea is, depending on what information I give you, some ways are more valuable than others. And depending on what you have, you might want to write it one way or the other. Always think about which way you want to write it. Think about what information you have. All right, so this is a good place to start. Have a great weekend.